first speaker of the day, and I called upon Dr. Slobodan Simonovic, Director of Engineering Work, University of Western Ontario, Canada, to deliver his keynote speech on flood impact maps, a standardized approach of understanding vulnerable landscapes. A few words only, a few words. Dr. Simonovic is globally recognized for his unique interdisciplinary research in system analysis and the development of deterministic and stochastic simulation, optimization, multi-criteria analysis, and other decision-making methodologies. His work is addressing challenging system problems lying at the confluence of society, technology, and the environment, and has been applied with a sustainable development perspective in water resources management, hydrology, energy, climate change, and public infrastructure. Dr. Simonovic has published over 650 professional publications, over 260 in peer-reviewed journals, and 3 major textbooks. He has delivered over 320 keynote and invited talks. He has been inducted to the Canadian Academy of Engineering in June of 2013, to the Royal Society of Canada in November 2020, and the Serbian Academy of Science and Arts in November 2021. It is my pleasure now to welcome a receive to the stage for Dr. Simonovic. The floor is yours.
Thank you very much. Hearing all these numbers is telling me only one thing: how old I am. I'm privileged and very honored to be with you today and start the conference by talking about relatively recent work done in Canada by my research group, looking into very significant question for the country, and I think for many countries around the world, flood mapping and basically improvement in the procedures for managing very serious floods. Conclusions of my presentations are here. I would like you to take that. This is what I'm trying to, and what I will try to present is kind of first-time application of very new information, globally available information that can help us understand the challenges of the floodplain mapping and standardizing the procedure across the very large regions for coming up with these particular tools. The conclusions of the kind of testing of the methodology and the procedure in Canada was showing that for the future predictions of the 100 and 200 year return flood events, the prediction and the climate impact is pushing the floods to higher magnitude and definitely increasing the frequency of the flooding. I'm very sorry, but having the procedure, having the methodology, and developing this type of products really does not have very high benefits if you don't have the procedure for communicating this information to general public. I was planning to demonstrate the tool. You have the website, and the tool is publicly available. We developed after this work the procedure that everyone can access the information obtained through this work, and I am extremely surprised with the results of that particular effort. I'll come to that a little bit later in the presentation and share with you the information. So I divided the presentation into kind of three parts. Tell you a little bit about the motivation, tell you a little bit about the methodology, how this flood mapping and how the standardized procedure is developed, and then maybe spend a little bit more time on the results or what these particular maps can be used for. The communication to general public, I'll just illustrate, and for those of you who may be interested, you can very easily access the site as well as, and also see the outcome of that work. So climate change is one of the factors in globally changing conditions. I usually put three of them together, the changes in population, either increase in population or the migrations of the population, the climate changing conditions, as well as the change in the land use, especially urbanization. These kind of conditions are really changing the way how the problems, especially problems relating to natural disasters, in particular case I'm talking about flooding, are kind of starting to occur. In the domain of the climate change, the Intergovernmental Panel for Climate Change, in preparation for the assessment report number 6, in August, not so late, basically a year ago, came up with a report that did review very large number of references and for the first time established very close and very strong connection between the climate changing conditions and extreme weather. And that was, I think, after the publication of that report, that was confirmed by first a number of events, and some of you may be familiar with some of them. In Canada, in November of last year, we had a huge flood that generated damage very close to $12 billion, not yet fully known. Very recently, the country of Pakistan experienced flooding that displaced about 33 million people and killed over 1,500 people. And the floods are happening almost all the time, almost everywhere. That did raise the kind of attention of at least our government in Canada, and this is one of the, I think, very important pieces of information where the government did realize that the existing tools, existing floodplain maps are not standardized. They are very different quality. They're utilizing very different data, and therefore it's extremely difficult to properly assess the risk on the scale of the country, and definitely develop the adaptation procedures, and as well as provide the investment that will be improving or providing the high level of protection. As you can see, the consequence of that was that government promised over 12 years to put about $1.4 billion in flood mapping activities, and with 4 important federal government departments with additional $64 million to start producing these maps that can be used with general public and everyone else who is responsible for managing floods in Canada. That's really encouraging and motivating, and this was kind of happening in the procedure when I already started developing this work and I already started investigating what kind of benefits we can find among the globally available information and also globally available data, so that we can standardize, especially over the very large region, the procedure that can give us the extent of flooding or the flood hazard, assessment of the flood hazard. Canada is the second biggest country in the world, and kind of having a procedure that can map the country like this is really demanding. So the project was proposed to look into different data, globally available data, to analyze the changes in flood inundation, to look at the impact of climate change on future flooding, and the support came from the in Canada, it's called the Natural Sciences and Engineering Research Council, which is a federal funding agency, as well as the sources indicate in this particular case, the reinsurance company that was interested in supporting this work. With a larger research team over about 2.5 years, we we started working on the project and developed the methodology that has been applied and shared with the professional community. I'm sorry for the overloaded slide, but I didn't have a chance to kind of do it differently. What you see is basically the map of the methodology. On the upper left corner are the main inputs that are being used in trying to assess the current state of the flooding. These are so-called publicly available reanalysis datasets. Reanalysis datasets are produced especially for the regions where you do not have very good coverage in monitoring and collecting the information, like the country like Canada. Northern part of the country is very sparsely gauged, whereas the southern part is done a little bit better. But the reanalysis products are combining the observations together with different tools, and then in a gridded format providing the hydrometeorological information for basically whole world. So what we have done for the first time, we tried to see how good and how useful this type of information can be in developing flood maps. So 4 different products were utilized. The main reason for selecting only these 4 was the overlapping period for which the data was available, and the period was from 1979 to 2010. The 3 of them, CFSR, EMERA, and R, are the American products, and ERA is the European product. All of them are basically utilizing the similar procedures in integrating the observations with the predictions, but as you will see, there are differences probably coming from not only methodology, but also the data and the way how the data is being used and processed in finally producing the information that in our case are the inputs into the analysis of the flood inundation. So from these 4 products, we utilize the runoff information. They are providing also the temperature, the precipitation, and evaporation and other hydrometeorological variables. But for the purpose of floodplain mapping, we stayed with the runoff information. And together with the development and availability of this publicly available data, we are facing also the situation where the global models are being provided and used in floodplain analysis. LISFlood is a very popular model from the UK. CaMa-Flood is another one, and we use that particular one, which is developed originally from University of Tokyo in Japan, and there are a couple of other models. These models are using the global information, integrating with the digital elevation information, water surface elevation, river data, and through this procedure, coming up with what is essential for us, basically the floodplain, flood depth, flood inundation, and that information is further in our work downscaled to grid of 1 by 1 kilometer, converted into the maps that can be now produced for the whole country. In order to kind of test the methodology and the procedure, we utilized the observed for 6 watersheds in Canada. We utilized the observed floods and flood events and compared with the maps to see how this globally generated information using the model on the scale of the country fits with, let's say, the real observations and events occurring at different locations within the country. So I'm just quickly going over this. The green dots in the upper graph are showing basically the density of the observations or the water water level observations in Canada, and I don't know, can you see the number of the letters at the bottom are the 6 locations of the 6 watersheds that we used for kind of verifying the model and modeling procedure. The information obtained from the methodology and through this verification process was really satisfactory. I'll show you some of the results. To quickly review the methodology, we usually start with basically downloading the runoff information, in particular case from the reanalysis products, and then at the station locations performing the comparison between observed and the reanalysis values. That was one way of confirming that the reanalysis products that we are using are applicable in our locations. Then we fitted the GEV distribution to the data, the global extreme value distribution, and in order to extract 100 and 200-year flood events. The reason why we selected these two only is that they are mostly used in Canada for kind of regulative purposes. 100-year floods are used to so-called establish the floodplain, and they are not allowing any development, or the government is not allowing any development within the boundaries of the 100-year floods, whereas the 200-year floods are so-called the flood fringe areas, where some development may be available, may be possible with the special approval of the water management agencies and responsible government departments. So these two are very important, and therefore we focused the whole work and analysis and mapping on these two particular type of events. At the end, we downscaled the information to 1 by 1 kilometer for the mapping and the presentation. In gray, you see the 3 additional steps that are used for the verification procedure, where we discretize the water depths into these 6 different basins. Then we clip the maps as well as did the comparison using common performance criteria. The criteria are listed here. That was the kind of hit rate, the false alarm, the critical success index, as well as the error bias. We also did divide the water depth into 5 categories from kind of low to high, and the results of the analysis are something like what you see here. Basically, the whole country covered by the information on the flood depth, inundation, and you can zoom in into any location, into any watershed. You can select the particular boundaries of interest. For example, select one particular watershed, and this is exactly what we have done for these 6 in order to do the verification. And then compare, let's say, the results, the existing flood information with the results. The comparison in this particular case, this is a Grand River in the southwestern Ontario, very close to the place where I live. And the Grand River, as you can see, is basically the difference between the green and red is the difference between the floodplain identified, produced by using our methodology, and red is the observed flooding, which is pretty high in this case. You can see the hit rate for a 100-year flood about 82.82, for 200.83, and for almost all 6 basins we achieved pretty good rate of agreement between the model and observed flood. That was a very fast walk through the kind of methodology and what we have done, in order to give you some time and show you what these maps can be used for. We decided to focus on the 3 different objectives in this particular case. The first one was to basically assess the water hazard across the country. Now we have a standardized procedure that covers the whole country, and we are now able to basically produce the maps for every possible location. You see the shades of, or the colors are showing basically the water depth. The maps can be produced for 100 or 200 year return period, and they're giving a pretty good indication where are the critical locations, where are the places where significant attention needs to be given, and where the hazard has to be minimized. The second objective was to see how this information on the flood maps can be integrated with other information to answer various questions. In particular question we got was how many people in Canada live in floodplains. And that's exactly what we have done in the second analysis. We used the floodplain maps generated, overlaid with the information on the population. The information on population is not continuous, so we had annual information from 2006 to 2019. Each graph is 1 year, and within this set of information, we were able to compare the kind of degree of exposure by census areas. Census areas are not equally spaced locations. They are obviously of much smaller scale in the highly dense areas like cities, and much larger in the outside of the urban areas. But that was the information that was possible to be utilized. If you look at the colors, the bright red are the kind of key locations where very a high level of hazard exists for the population living in these areas. We are talking about southern part of Ontario. We are talking about western part of Canada, exactly where the flood was occurring in 2011. And we are noticing that the northern, obviously, areas are not of the high degree of exposure. And not only that it's not of the high degree, but it's actually reducing. If you look at from 2006 to 2019, it is the exposure is changing. So this type of analysis gave us the feeling, and also the information how many people may be vulnerable. I can give you some numbers, but Canadian population is around 37 million people. About 3.8 million people live in 100-year floodplains right now, which is a pretty significant number for the country, and therefore I think very serious attention should be given to managing these floods. And the third application was the impact of climate change. This was a very significant part because the reinsurance company that funded the project was very much interested to look at the future and future climate conditions and see how these future climate conditions will be affecting the flood hazard. Canada is a very specific country. We do not have yet fully flood insurance. The main reason is it's a very large country, a very small population, and therefore the insurance companies are claiming that the cost will be very high. However, with the flood of 21, 2013 in Calgary, the situation started changing. The insurance companies are getting into the flooding, and right now, very serious dialogue is established between the government and insurance in order to find out the best model, combining public as well as private funds in using insurance as one of the measures for spreading the risk. How did we do the climate impact analysis? Using the very similar procedure to the methodology that I already introduced, but instead of utilizing the historical information or the reanalysis data sets, we use the climate data produced by 17 different models. We use the most recent products, so-called the CaMa-P6 coupled model intercomparison project, which offered for the first time the runoff information as output from the global climate models. So without using the kind of hydrology and hydraulics, straight from the climate models, we were able to download the runoff information, plug in the runoff information into our hydrodynamic model, CaMa-Flood, combine with the digital elevation, river and other data, do the calculation of the river channel depth, flow velocity, and extent, downscale that again to 1 by 1 kilometer, and produce the flood maps for different climate conditions. Because different models are giving you definitely different input, we decided to look multiple options. And at the top you may see we use the historical period as one interesting part so that we can compare to reanalysis analysis from the beginning. We use the near future, 2020 to 2060, and then the far future, 2061 to 2100. And for each of them, because climate models are being run for different emission scenarios, we used two scenarios. The most recent scenarios are so-called SSPs, and SSPs are shared socioeconomic pathways, and two of them we utilized 4.5 and 8.5. 4.5 being something like intermediate future conditions of the socioeconomic development of the world, whereas 8.5 was very extreme scenario, and we wanted to see the difference. That type of analysis was very informative, gave us opportunity, for example, to look at the hazard in different river basins across the country, and the color of the scale is showing you percent change, pointing out that many locations in Canada are going to face, under the changing climate, pretty significant increase in flood inundation. This is a very important piece of information. Some of these basins are highly populated, some are less populated. Lots of funds are required to provide a kind of protection for the people and ensure that future floods will not generate very high economic damage. The second output was the kind of climate change impact on the flood depth, or basically the level of hazard that you can kind of measure by, again, the color scheme indicating with red very significant change, going up to 60% increase in different parts of the country. Again, mostly southern parts being exposed to increase in hazard and increase in frequency, and northern parts and both coasts are showing a little bit different results. For the coastal areas, I am hesitant to say that our results are very reliable, because in the coastal areas you have the other river focusing here mostly on the fluvial, or basically riverine flooding, whereas the coastal areas may be affected by a combination of the riverine precipitation and tide events, and therefore one of the plans is to extend this modeling effort to the coastal areas and improve our assessment in that area. And the final result was change in the flood frequency. What you can see for the two scenarios, for the 100 and 200 year, again, the increase in frequency, red showing increase in frequency, blue decrease, mostly around the areas where most of the population lives in Canada. The results are confirming what I think the country is experiencing, and therefore I think we have to very much look into the review of the standards for the design, planning, management of the infrastructure, because everything, at least in Canada, is regulated using something like 100 year or 200 year or any return period flood as a kind of event, design criteria event, and this type of analysis showing that basically return period is changing and changing significantly, and therefore what was 100-year flood today in 10, 15, 20, 30 years may become 30-year flood or 10-year flood. And that's a very significant message that was coming from the analysis. There is something on my screen that you don't see. Okay. And let me touch on the final, I'm not sure what is happening, but touch me on the final communication part of our work. We completed this work somewhere in November of last year. That was a period of the COP meeting in Glasgow, and I thought it's a good moment to try and share this information with at least Canadian public, and also use the attention on the climate change, which was going on together with the meeting there. So we developed a kind of web interface that stores all the maps that I was mentioning, maps developed to capture the current state utilizing the reanalysis data, maps that are capturing the future conditions. I kind of reviewed very quickly, and provide explanation about the methodology, provide a kind of information how the maps can be used, and we posted this onto the website, and you would be, or I was shocked. In about a week, we got 11 million hits to that particular site. It's definitely coinciding with flooding in British Columbia that was occurring in November and the COP meeting. But that kind of attention, especially because this was only for Canada, was really, really overwhelming. What we are finding now that like 25,000 people are regularly basically using the maps. I was receiving emails like, can you tell me, I'm planning to buy the house in this particular location. Is there a way that your maps can help us and answer the question, will this particular location be, hazardous location or not? And many other questions. The tool is very straightforward, friendly. It provides the kind of Google Map type of background, as well as so-called the OpenStreet background, where the OpenStreet background includes actually the location of the properties. So you can basically easily overlay the flat maps with the information of the topography, the information of the location of the properties. Insurance people, as well as the government, were very much interested to see how different areas are affected, because they are usually providing this, they're analyzing that on the scale of so-called the postal codes. This is the map of the postal codes. Under the map, the yellowish orangey is basically digital elevation model. We have two of them, very detailed and less detailed. And very easily you can kind of click on any location, and for the particular information that's available, you can see, for example, the coordinates, you can find out the elevation. And if you select from the upper menu, you see the current conditions as well as the future conditions. These are the menus that are listing all the maps that are available. And by selecting the map, you are overlaying the flood conditions. This is a picture produced for London City, where I live. This is downtown, the north-south Thames and the Thames River. From downtown flowing, different shades of blue are giving you the basically information about the water depth, and the blue areas are indicating the areas that are being inundated. So if you use the OpenStreet background, you can actually see the properties and select information about the particular properties. We cannot answer the question how deep will be the water at your doorstep, because the OpenStreet maps do not have the elevation data. They only have the kind of footprints of the. So this type of maps are kind of available for 100-year, 200-year, current, near future, and far future. Some manipulation of the data is possible. You can select the area. You see in this particular location, you have the coordinates, you have what type of map is showing with the blue, what is the resolution, digital elevation, as well as the postal code for that particular location. So anywhere you click, you have that opportunity. You can clip the area. You can download the whole map onto another tool if you would like to process this information, or you can only download the area that's selected for the further analysis. This is the kind of way how the maps are provided. You see the downloading options, clipped or full, the type of, the list of maps that the system includes, and some information about the software being used, as well as details of the methodology, together with basically step-by-step instructions how you can utilize the tool and how you can use this information for your analysis. So let me finish with pointing out what are the specific aspects of the methodology. I think for the first time we were able to have a standardized methodology to cover the whole country. This is definitely the number one, I think, advantage. This is the country of 10 million square kilometers, and you can realize how significant is, something like that. The second important, I think, characteristic is use of the publicly available data, especially the reanalysis information, and in the comparison of these 4 different reanalysis tools, we identified one NAR, North American reanalysis analysis, which is at least for our condition, showing the best results. Use of other publicly available information for hydrodynamic modeling, like a global digital elevation model, river data, global water data, OpenStreet, and so on, is also fully tested and integrated with the methodology. And the modeling outcome was, I think, possible at the level of 1 by 1 kilometer for the flood depth, flood inundation, and flow velocity. For the first time, we utilized the, I think, most recent climate modeling data and climate modeling information. We did provide that for the near and far future. We looked also in the flood frequency and the change of the flood frequency. What we are recommending for the kind of future activities is to use this information and create a kind of national flood hazard atlas, perform the detailed exposure analysis. This is now very highly on the priority of a couple of federal departments. And as I pointed out earlier, including the coastal floods in the analysis. I am currently working with 2 departments, Department of Public Safety and Natural Resources Canada, to export this methodology into their offices, so that they can continue using the Canadian data, using the methodology, and making this information publicly available. And you will be surprised. They are doing this analysis, but they're doing it using the commercial product. And by using the commercial product, they have all the possible limitations of providing this information to general public. So, having something like this, standardized methodology, globally available data, is going to help them, I think, go over that step and share the information with the general public, as well as everybody else who may need this information. Thank you very much for the time. I'm very happy to answer some questions if there are some. This is the list of the publications that came out of this particular work. Everything is available for free from my personal website. You can search by publication, you can search by topic, and also you can have access to the tool and the address of the tool, floodmapviewer.com. Thank you very much.
Thank you, Dr. Simonovic, for this most interesting lecture, and we have time for only one, at most two, very short questions. Please raise your hand so I can come to you as quickly as I can.
I'm sorry for using the time.
Thank you. Alvarez from National University of Mexico. You made some inferences about 100 and 200 year predictions. Now, the question is, how are you going to modify this data with the changes that are occurring so fast in these days? I mean, a general comment on that would be welcome. Thank you.
Yeah, that's a very valid question, and I think this particular question deserves very serious research effort. Your question is, is the 100-year flood really going to be 100-year tomorrow, or is it going to be 50 or 35? So the only tools we have right now are the global climate models. They're predicting the future conditions. They're predicting them in a way of number of different scenarios, emission scenarios, as well as the methodologies that different climate modeling agencies are using. So what I'm usually recommending for the practical application is to run multiple future scenarios, multiple futures. See how this will change. What will be the range of change? For different locations, we may have a very different range of change. For the City of London, we did that, and the 100-year flood is changing from 30 to 80-year flood. So that range of uncertainty, which comes from the fact of using different climate models in different scenarios, is an important piece of information for those who are making the decisions, what will be the design standard and what will be used in the future.
Thank you very much. We have to move further, but when the 35 we have a break, our first coffee break, and then we can put more questions and talk to Dr. Simonovic. I call upon Dr. Nick Barton from Norway to deliver